So today we're going to talk about how to describe and explore data. So our goal is to explore and describe the characteristics of our sample data or the data that we have in front of us, wherever that data came from. And we are going to attempt to describe the characteristics of this data set through visualizations and through summary statistics. So with respect to visualizing and plotting data, I'm going to go over each of the main ways that you'll commonly see. And all of the ways that I'm going to describe are ways that we would visualize a single variable at a time. So we'll talk about like instances, what we call univariate descriptive statistics. It just means that we're only interested in examining one single variable from a data set at a time. You can do all of the variables individually, but you're only doing them one at a time. So for example, if we have data on both the department and the age of employees, right, we would do these separately for everything that I'm about to talk about. In future videos, we'll discuss multivariate techniques. So back to the visualizing and plotting data, the first technique we'll talk about is the frequency distribution. And frequency distributions, they're really the most basic form of visualizing and plotting data, and they can be used for both quantitative and qualitative data, so both numeric and categorical data. And they're really simple. Basically, you just list each unique value or category in your data set for a given variable and the number of times it occurs. So if we have data on employees and we're looking at the department that they belong to, that's the variable that we're interested in, well, we would plot it as each of the three different values that we have for department and then the number of employees that fall within each of these departments. If we have a numeric variable, it gets a little trickier because then we would have to list out every single possible unique numeric value that we have in our data set and the number of times that value occurred. It doesn't look that bad with this example because I've only included ages from 18 to 29 and everybody's age is rounded up. But imagine how difficult this can get once we start having numeric or continuous variables where we have a ton of different values. So like think about employee salary, for example. Well, think about all of the different ranges and unique values that people's salaries could be. And if you try and list all of those out from smallest to largest and the number of times those occur, not only is that really, really difficult to do, but it's really not all that meaningful. So frequency distributions, they don't really do a good job of describing quantitative data, but they're still important to understand because they really form the basis of a lot of the other things that we're going to be talking about. So the next technique is called a histogram, okay? And this is similar to a frequency distribution, but it's only for quantitative data. And now we don't list each unique value, we group adjacent values or values that are next to each other instead. And we do this to help display trends in the data. And we'll use the example of daily pay rate. So you see in both of these histograms, we have the daily pay rates of employees. It looks like they range from about 0 to roughly 1,600. And instead of trying to list out every single pay rate of every single employee, we've grouped them or put them into bins of adjacent values. So for example, this bin right here might represent the employees who make between like $100 and $120 a day. The next bin might be employees who make 120 to 140, 140 to 160, so on and so forth, right? But the important thing is that we are grouping adjacent values so that each bin represents a little grouping of values that are close to one another. And this allows us to focus on trends and patterns instead of getting caught up in trying to look at every single unique value, because that really wouldn't be that meaningful in this example. Now, one thing to be aware of is that your choice of bin width, or basically how wide the interval that each bin or each group contains, that choice can really change the way you see your data, the way that your histogram is visualized. This is the same data set, and there's two histograms that are pretty different, right? And it's because in this bottom one, the bin width looks to be about 200. So everybody who makes between maybe $50 and $200, and then 200 to 400, or whatever the case may be, right? I mean, the bin widths have to be equal, so that wouldn't work. But maybe like 0 to 200, 200 to 400. Either way, they're clearly wider than this top histogram. And so when we do this, this histogram looks pretty different from this one up here. So it's important to recognize that with histograms, the choice of bin width can really change the way your data looks. But still, it's a really, really popular and a really good way, a really simple way of displaying trends in data. This is a lot more meaningful than trying to plot every single possible pay rate that's in our data set and the number of employees that get that exact pay level. Moving on to kernel density plots. So this is kind of a step up from histograms in terms of basically this notion of trying to focus on trends and patterns. Kind of like with the difference between a histogram and a frequency distribution was instead of focusing on every single value, we grouped values. Well, going from a histogram to a density plot, now we're attempting to fit a smooth curve to our data values. So instead of literally, like, imagine if you're looking at this histogram and you tried to trace along the line of every bin and tried to make like a line that way instead of the smooth curve we see up at the top. Well, if we look at the density plot up here, we can see that we've smoothed out a lot of this variation that we would see in the histogram. So we are losing some of the detail that we have in our histogram, but it's an attempt to help obscure noise, right, and focus on trends and patterns. And so the basic idea is that each actual observation could have been slightly different, and we shouldn't treat this as being, exact. We shouldn't be overly precise. So as an example, the daily pay rate could easily be 810 or 820 instead of 815, right, for a given observation. And so kind of like how a histogram would group the values between 810 and 815 together possibly, or whatever the interval is that we choose for the histogram, a kernel density plot takes a slightly different approach and instead tries to plot possible values that could have occurred for each actual observation. And so if we look at this down here on the bottom, hopefully this makes a little more sense. Each of these little mini curves, they represent individual data points. So the peak represents the value that actually occurred. So here we had a value of x equals 0 for just some imaginary variable x. And then the curve represents what possible values we think this actual observation could have taken on. They're within reason. So we see that, most of the curve is, focused around the value that we actually saw, but then it also allows for the possibility of seeing some other values that are close by. And so with the kernel density plot, the idea is that we do this for each of our actual observations. We plot these little mini curves, miniature curves, over each of our actual observations to display, values that they could have taken on instead. And then once we've done that, we then fit an overall curve where the height of the curve represents whether or not the individual curves are kind of like stacked on top of one another or very close to each other. So for example, if we look back to our individual curves and we see two curves that are peaked over x equals 1, and then another one that looks like it's peaked over 1.5, and then 1 over 2, there's quite a few values that are in this range, so the overall probability of seeing values in this range is pretty high, right? Or another way of saying this is that there is a high frequency of values that could have fallen within this general range instead of just thinking of it as being 1, 1, 2, 1.5, etc., right? So we're just saying for each of the values we actually have, let's plot what those values could easily have also been instead, and then let's fit a big curve that kind of takes into account the overlap in these little miniature curves. And then basically we see that is the case up here as well. So with our histogram, we have kind of smoothed out some of the variation that we see in the detail that we see in the histogram, and instead we have a more general display of this pattern. Moving on to the stem and leaf plot. So stem and leaf plots represent kind of like a compromise between histograms and kernel density plots, or KDPs. So with both the histograms and the kernel density plots, we lose track of the actual values, but we keep track of the trends, whereas the frequency distributions obscure the trends. We can't really see like general patterns, but the frequency distributions do keep track of the individual actual values. So stem and leaf plots attempt to kind of like compromise between the two, sort of, and in the sense that they're kind of like a middle ground where we can see both the actual values and an overall trend. And if you look at a stem and leaf plot up here, this is a stem and leaf plot that corresponds to what we see in our histogram down here. And if you tilt your head and look at the stem and leaf plot sideways, it kind of looks like a histogram flipped over on its side, sort of. But we can see the actual values that actually occurred. And so the way you read stem and leaf plots is that the first digit is the leading digit, what we call the stem, and then the second digit is the trailing digit, or the leaves. Now, it's important to note what unit of measurement your leaves are in. In this example, we have daily pay rates. So the leaves represent tens, and then the stem represents hundreds. So, for example, this first row of our stem and leaf plot. Okay, the leading digit, or the 1, that represents 100, and then we have an employee who had a daily rate of 100, a daily pay rate of 110, 110, 110. So there were 3 employees that had a daily pay rate of 110. Then we have looks like 1, 2, 3, 4, 5 employees who had a daily pay rate of 120, 4 who had a daily pay rate of 130, so on and so forth. So we can still see this trend in our data, this pattern, but we don't lose sight of the actual values. It's just important to pay attention to, what exactly units both your stem and your leaves are in. A lot of times you'll see this be the tens digit and this be the ones digit. So it really just depends on the scale of your data, right? So we covered some of the basic plots. We haven't covered box plots, which I'll cover towards the end for a good reason. But now let's take a quick digression, and instead we'll talk about some general ways of describing data. And so the first category of descriptive techniques that we'll talk about, or ways we can describe data, are the general shapes that our data distributions can take on. So the first characteristic we might be interested in is in the number of predominant peaks, or the number of peaks of our distribution of values. So if you think about our frequency distribution, where we see basically, or our histogram where we see the number of times each observation occurred, the peak shows us which values were the most frequent. And so there's this notion of modality where we're wanting to know how many peaks do we have. Unimodal would be 1 peak, bimodal would be 2 peaks, multimodal would be 2 or more. And so with bimodal data, what we see is that there are 2 ranges of scores where we have equally high frequencies. With the unimodal distribution, we see that the majority of our scores actually fall within 1 concentrated area. So the number of peaks, again, is what we refer to as modality. When we talk about symmetry, we're interested in whether or not our distribution has the same shape on both sides of the center or not. So data can be symmetric, like this right here in the top left. It's got the same shape on both sides, if you imagine drawing a line right down the middle. Or it can be skewed. And then within skewed data, we have positive skew and negative skew. Here we have negative skew, and we always talk about the direction of the tail, or the trailing off. And so when we have skewed data, we have the majority of our scores that fall in one area, but then we have some extreme scores that trail off or pull the distribution in the other. And so you talk about the direction of the skew in the direction of where the extreme values lie. So this is negatively skewed because the smaller values are more extreme and they're pulling our data that way. And then we have positively skewed because these more extreme values are the larger values, the more positive values. And then we can also talk about something called kurtosis, which is basically the concentration of scores in the shoulders or the tails of our distribution. Now, when I say shoulders or tails, we'll start with the tails. That's the easiest to describe. The tails are literally kind of what you would think, the tails. The shoulders would be kind of like up here, bunched up in the shoulders, and then the peak would be kind of like the head, if you think of it in terms of like body parts, right? And so kurtosis, we're talking about the degree to which our scores are bunched up in the shoulders or the tails of our distribution. And there's three general categories or descriptive categories of kurtosis. If a distribution is platykurtic, then we're saying that there are relatively few or no tails, and most of our scores instead are bunched in the shoulders. That would be platykurtic, and that would be this right here. We also have statistical values for both skew and kurtosis that we'll talk about. So we actually have a quantitative measure of these characteristics, but we also have like categories and ways of describing them as well. So I'm talking about right now the general descriptive characteristics, and then in a little bit we'll talk about the actual statistical values that you can compute. But when you have something that is negatively skewed, that would be a negative skew value. The skew statistic would be negative. And then if it's positively skewed, the actual skew statistic will be positive. With platykurtic, where we have low kurtosis, the kurtosis value would be negative, and because we have a low concentration of scores in the tails. When it's mesokurtic, then we would say that it's normal or well balanced, and that would be like this up here. And then when it's leptokurtic, we would say that there are fat tails, and that would be a positive kurtosis value, and that would be right here, a leptokurtic distribution where we have fatter tails. If you compare the leptokurtic to the platykurtic, you can see that with the platykurtic, the tails really are kind of skinny, more of the scores are bunched in the shoulders, and then that's the opposite with this leptokurtic where we do have tails. So the modality, the symmetry, and the degree of kurtosis, these are all ways that we can describe the general shapes of our distribution of data. And then, like I said, we can also move into actually quantifying ways we describe our data, and that's through summary statistics. Remember, when we're talking about our actual observed data, we talk in terms of statistics. When we talk about the characteristics of a population, then we're talking about parameters. So the first characteristic of summary statistics is that pertaining to central tendency. And this is these are just measures that reflect where on the scale the distribution of scores is centered. So the mean is just the average value. Okay, well, the mean is susceptible to extreme values. You see down here in this little visual I have, when you have skewed data, most of your scores fall in one area, and then you have some extreme scores that pull the distribution in the other area. So there's not many scores that are extreme and small in this figure right here. Most of the scores are relatively larger over here, but these smaller extreme values are pulling our mean over in the direction of the skew, right? So the mean is susceptible to extreme values. Whereas if you compare it to the median or the mode, those are not susceptible to the extreme values, right? So our mean it's being pulled by extreme values, even though most of our actual observations are over here. And then if you had positively skewed data, you would see the mean being pulled in the positive direction instead. So that's the weakness of the mean, is that when you have extreme values, that can pull your mean in a direction that's further away from where the majority of your scores are. The median is just the midpoint, right? It's literally just the middle data point, and it's the point at which 50% of your scores fall above it or below it. So if you imagine ordering all of your scores from largest to smallest, and then just starting at the small end and at the high end, and then just counting towards the middle, the median is literally just the middle score. So it's not vulnerable to extreme values, because if you think about it, the values don't really matter. The only thing that matters is just that middle value, right? Because you're literally just counting inwards the number of spots until you reach the middle of your scores. It doesn't matter what those actual values are until you get to that single midpoint that you're interested in. And then the mode, that's the easiest one to understand. It's just literally the score that occurs the most. And it's always a value that actually did occur in your data. And then here we have some examples of the mean, median, and mode. I won't spend too much time on it, but the mean, which in the sample version is x bar, well, it's just the sum, sigma, that's the notation for the sum of all of our x values, all of our observations. So the sum of all of our observations divided by the number of observations. And there's a worked out example. Then we have the median. Well, to find the median, you actually find the median location, and then you just count inwards to that location. So what I mean by that is the formula for the median location is n, the number of scores, plus 1 divided by 2. So if we're looking for the median of the values 2, 3, 4, and 5, well, our median location is just n, which is 4. We have 4 data points. N plus 1, so 4 plus 1 divided by 2. So our location is the 2.5th data point. When you have an even number of scores, your median will fall between two different scores. Whereas if you have an odd number of scores, then it'll just be the actual value in your data, right? So for this example, the location was the 2.5th data point. So what we would do is we would count inwards 1, 2, and then 2.5. So it falls in the middle of our second and third value. So that would be between 3 and 4, which would just be 3.5. And then when we find the mode, this is actually a typo. I have an extra 2 here, as you see. I'll correct this in the PowerPoint that I post. But imagine that it's just 2, 3, and 4, and 5, like the other examples that we have. Well, in that instance, each value occurs once. So that would be an instance where we have what we call a uniform distribution, where all the values occur the same number of times. If we had the example where I had this typo and we had instead 2, 2, 3, 4, and 5 as our scores, then our mode would be 2 because 2 occurs more than the other values. So again, I'll fix that typo in the PowerPoint that I post. So now let's talk about variability. There's the two most common measures of variability are the variance and the standard deviation, and they reflect how much observations deviate from their average. So in other words, right, when we find our average, sometimes our scores may be clustered around their average, and then the average really is informative about, the majority of our scores. It's representative of a lot of our scores because most of them do fall near that average. In that instance, we would say that we have a low standard deviation or a low variance because there's not that much of a deviation of the scores from their sample average. But if the scores instead are distributed over a wide range of values, well, then that average isn't as representative of the full set of scores anymore. And we would say that there's a high standard deviation because they do deviate from their average to a greater degree. And so as an example, let's look at this figure down here before we talk about the formulas. This notation, sigma, this is the notation for the population standard deviation. For the sample, you use little s instead, but just note that this just means standard deviation. So what we have here is we have 3 distributions with different standard deviations, but they all have the same mean. So the mean looks like it's right at 100, and when our standard deviation is 5, which is the smallest standard deviation, a lot of our scores do fall around our mean of 100. So that average is more reflective of our full set of scores, and we have a low standard deviation. The scores aren't deviating very much from that average of 100. Then as we increase, we go to the pink line and then the red line. When we go from a standard deviation of 5 to 10 and then to 20, we see our scores getting more and more spread out, and they deviate more from their mean, from their average. So that average doesn't reflect our full set of observations anymore. Another way to think about this is that if we are trying to estimate values, right? Well, if we have a large standard deviation, that means we're less certain about our estimate because the actual individual values are spread out quite far. They deviate a lot from that average. So the standard deviation is a measure of uncertainty. The higher the standard deviation, the less certain you are. And then the variance and standard deviation are both very susceptible to extreme values. And we'll see that when we calculate the variance and standard deviation, why that is. But they are very much affected by extreme values. And so up here, we have our formulas. And I have another slide that goes over how exactly or what exactly this stuff means. But whenever you see variance, I like to think of it as basically the average squared deviation. And then the standard deviation is just the square root of the variance. So what we see here is, like I said, when we talk about the sample variance, we use little s, so it's little s squared for the variance, and then little s not squared, or the square root of the variance, for the standard deviation. So s squared for the variance, s for the standard deviation at the sample level for both of these. Well, our variance is the sum of the squared deviations of each observation from its mean. So x minus x bar, remember x bar is the average, x represents the individual observations. So the variance is the sum of the deviation of each score from its mean, the sum of the squared deviations actually, divided by n, the number of observations, minus 1. So it's roughly equivalent to the average of the squared deviations. And this will make more sense once we work it out in just a minute. And then the square root of that is just the standard deviation. So here we have an example of how to calculate this. So let's imagine we have a variable x, and we'll just say that it's the number of years that employees have on the job. So we have 5 observations, and the values are 2, 2, 4, 1, and 5. Well, the first step is to calculate the sample average. Okay, these are our actual values. Well, our sample average works out to 2.8. The sum of our values is 14, and then the average is 14 divided by 5, because we have 5 observations. So we get an average, a sample average, an x bar of 2.8. Then we calculate the deviations of each observation from the sample average, or x minus x bar. And so it's just each individual observation, x minus the sample average, x bar. So 2 minus 2.8, and then so on and so forth. Now, when you see a negative deviation, well, that represents that the sample average was larger than the actual observation. So this would be a below average score because the average was bigger than the actual observation. When the observation is above average, then our deviation will be positive, like this one. So here we see 4 was the actual observation. 4 minus 2.8 is 1.2. It's a positive deviation. The reason I mention this is because if we were just to add these up, the positives and the negative deviations would cancel out. And so when we add them up, you can check this out for yourself, it adds up to 0. So we need a way of accounting for the fact that when we calculate our deviations, we can't just get the average deviation, because when we go to calculate our average, the positives and the negatives will cancel out. So instead, we square the deviations. So we just take each deviation that we calculated here, and then we square it, and because when you square a negative number, you get a positive number. So now all of our values, our squared deviations, are positive. And so then we add them up. So that's why we use squared deviations. It's just because if we didn't do that, then the above average data points and the below average data points, well, those would give us negative deviations and positive deviations, and those would cancel out when we go to add them up. And so when we add up the squared deviations instead, that works out to 10.8 in this example, and that's the numerator, the top part of our formula. So then we just need to divide by n minus 1. So again, the sum of our squared deviations was 10.8, divided by n minus 1 to get our sample variance. N is just the number of observations, so it's 10.8, the sum of our squared deviations, divided by 5 minus 1, which works out to 10.8 divided by 4, which works out to 2.7. And then the sample standard deviation is just the square root of our sample variance. So we just take the square root of 2.7, and we get 1.64. Okay, so we covered the variance and the standard deviation. Now we'll talk about another measure of how the data are spread out, and that's what we call quantiles. So You've probably heard of quartiles and percentiles, and maybe not quantiles. Well, quartiles and percentiles are just a specific form of quantile. And all a quantile is if you order your values in your data from small to large, and then you split your data set into a certain number of equal pieces, n equal pieces. And that's up to you. You can choose how many equal pieces depending on what you're interested in. So if you want to split it in your data set into n equal pieces, you use n minus 1 cut points equally spaced out. So if you want quartiles, if your goal is to split your data into 4 equal pieces such that there's 25% of your scores fall in each quartile, then you would use 3 cut points, right? If you just want 2 pieces, then you would just have 1 cut point, right? You just cut it right down the middle, and then you have 1 cut point and 2 equal pieces. But with quartiles, this gives us 4 equal pieces that each contain 25% of the values or the observations in our data set. So the first quartile marks the lower 25%. The second quartile marks the 50th percentile. And the third quartile marks the 75th percentile. And then above, Q3, the third quartile, above that, falls the range of scores between the 75th percentile and the 100th percentile. So again, with quartiles, you're just cutting your data into 4 equal pieces that each contain 25% of your observations. And then with percentiles, then you split the data into 100 equal pieces. So when you hear someone say they're in the 99th percentile, well, that means that they have a score that falls above 99% of the other observations in your data set. And then we have an example here. So on the bottom we have a histogram, and then I have some various quantiles that would correspond to our data set up here on top. And so this first one, this represents the 10th percentile. This represents the 25th percentile, the 50th percentile, which again is the midpoint or the median, and then the 75th percentile, and then the 90th percentile. So 90% of the scores fall below the 90th percentile, 75% fall below the 75th percentile, 50% fall below the 50th, and then so on and so forth. And then we can use this knowledge of quartiles to talk about the range and the interquartile range. Well, the range, you really don't need to know quartiles for that. The range is just a measure of distance from the lowest to the highest score. But the range suffers heavily from extreme scores. So imagine that you have 1,000 values or observations, and all 1,000 of those fall between 0 and 1. So your range would be 0 to 1. But just one single value of 100 will now change your range from 0 to 1 to 0 all the way to 100. So even though you have 1,000 scores that fall between 0 and 1, just one observation, one extreme observation, can drastically change your range. And then we already talked about quartiles and what they are. The interquartile range, that's an attempt to kind of get around the vulnerability of the regular range to extreme scores. So recognizing that an extreme score can change our range, one way we might try and fight this is to use the interquartile range. And what that does is that only looks at the middle 50% of the score. So the middle 50% of the scores, rather. So it's a measure of distance from our 25th percentile to our 75th percentile. So if we go back here, right, using this example, here's our 25th percentile, here's our 75th percentile. This is our interquartile range. It's what falls between our 25th and our 75th percentile. It's also the middle 50% of our scores. So 50% of our observations, the middle 50% of them to be precise, fall between our first quartile, the 25th percentile, and our third quartile, the 75th percentile. And then we see that here where I have a histogram of hourly pay. So the range of the hourly pay would be from 0 to 10. I guess there's some people that maybe work pro bono or something like that. Obviously, this isn't realistic, right? But then we would see, using this example, right, that our Q1, our first quartile, would fall right here. So 25% of our values fall at or below 2. Our second quartile, which is our median, is 50%. So 50% of our values fall below at or below value of 3, it looks like. And then our mean would be 4 in this example. Q3 would be right here. This would be the 75th percentile. So 75% of our scores fall at or below 6. And then the upper 25% fall above Q3. One note, you see here that this data is skewed. Well, this makes sense because look at our mean. Our mean is above our median. Our median, which is our midpoint, is Q2. That's the 50th percentile. Our median looks to be about 3. But our mean, because our data is positively skewed, our mean is pulled above our median. It's greater than our median. So that's an illustration of how the mean is susceptible to extreme values or skewed data. And then here's some examples of how this would be worked out with actual data. And I won't go over that. You can go over that yourself. And then now we'll talk about box plots. So box plots are really common, and they're really useful. And so before I go over the text here, I just want to talk about what we're looking at right here. So this is a box plot of a skewed data set where I have monthly income for a bunch of employees, and then I've divided it into the monthly income for males, which is the turquoise color, or the men rather, and then the monthly income for the women, and we see that peach color. And so this is, don't be freaked out by seeing two box plots. It's just one data set where I have a box plot specifically for the income levels of the men and the income of the women. So same concept, right? It's still a box plot. It's just there's two of them because I've looked at this both for men and women separately. So box plots are another form of data visualization, and they really allow you to focus on the spread of your data. So what you have with the box plot is, well, let's just look at the box plot. Okay, so where my cursor is, the box itself covers the middle 50% of your scores, which we know from our earlier discussion is the interquartile range, and it's the Q1 to Q3 range, right? So we have the lower edge of our box, which is the 25th percentile or the first quartile, Q1. Then we have the upper edge of our box, which is the Q3, the third quartile, the 75th percentile. So the box contains the middle 50% of our scores. Then we have the median line right here, which is the second quartile in the 50th percentile. Don't get the middle 50% and the 50th percentile confused. The 50th percentile is a single data point that marks where 50% of the scores fall above or below. It's the midpoint. The middle 50% is the entire middle 50% of your observations that falls between the 25th percentile and the 75th percentile. So that's the box. Okay, well, then we have this notion. First, I'll talk about this notion of inner fences. And what the inner fence is imagine that you start at Q1 and then you go out 1.5 times whatever your interquartile range was. Well, our interquartile range, remember, that's the range of Q3 to Q1. So whatever Q3 minus Q1 is, that's your IQR, your interquartile range. So if you multiply that interquartile range by 1.5, well, you go out from Q1, you go down by 1.5 times your interquartile range, and then from Q3, you go up by 1.5 times your interquartile range. So your inner fences is what they, that's not my terminology, that's what they're called. That's just going down from Q1 by 1.5 times whatever your interquartile range is, and then up from Q3 by 1.5 times whatever your interquartile range is. And so again, it's just a method of it's an attempt to account for the spread in your data, right? Well, the adjacent values are the actual data points that you actually have that are no more extreme than your inner fence. Because the inner fence, which is again Q1 minus 1.5 times the interquartile range, and Q3 plus 1.5 times the interquartile range, there's no guarantee that's an actual observation. right? It's just your Q1 minus 1.5 times the IQR, and then Q3 plus 1.5 times IQR. There's no guarantee that's an actual data point. Well, the adjacent value is an actual data point, and that's the actual data point that doesn't go outside of the inner fence. So imagine that you have a fence surrounding cows. Well, the inner fence would be, the fence that surrounds the cows, but then your lower and adjacent values, or sorry, your lower adjacent value and your upper adjacent values, those would be the cows that are closest to the fence on both the low end and the far end of the pasture. I know that's a ridiculous example, but that's the easiest way I think of it. So your inner fence doesn't necessarily represent an actual data point, an actual cow. It just represents, the confines, right? Whereas the lower adjacent value and the upper adjacent value, those are the most extreme actual values that still don't fall outside of that fence. So the cows that are closest to the fence on the upper and the lower end. And the reason we care about that is because, again, those are the actual values that don't exceed this imaginary fence we've set ourselves. Well, once you go outside of that fence, right? So the first data point that is outside of whatever your upper adjacent value and your lower adjacent value is, those are the outliers. So that's why we care about these upper and lower adjacent values. They set the bounds basically for the outliers. So the outliers again are all the points that are more extreme than the adjacent values. The whiskers, these things right here, these are just the lines from Q1 to our lower adjacent value, which would be right here, and then Q3 to the upper adjacent value, which would be right here. And then the outliers are any data points that do fall outside of that. So I know this is a lot, but just as a recap, our goal when we are describing and exploring data is to describe the variables in our sample data through visualizations and summary statistics. And everything that I've covered so far has been, for the most part, how to do one variable at a time. When we saw the box plots, we did see how we could look at, a variable like hourly pay rate by gender levels, but we're still concentrating on one specific variable for the most part. These are all what we call univariate descriptive statistics. So this is usually the first step that you would probably want to take with your data set, right? Investigate the the values that you have for each of your variables and see how they're distributed and get a feel for what it is you're looking at. So visualize this through frequency distributions, histograms, density plots, and stem and leaf plots, and then calculate your actual summary statistics that deal with your measures of central tendency, which is where the center of your distribution is, and then the measures of the summary statistics for the measures of variability and spread, how spread out your data are from your average or your midpoints. And then you also want to look at your symmetry, which are your values of skew and kurtosis. And so as an example, I included a table that would list, just the descriptive statistics, the summary statistics for some imaginary variables. And this might be a list of like the things you might want to look at. So for each of these variables, age, pay, distance, and tenure, we might want to know what the mean, the median, the standard deviation, the variance, Q1, Q3, IQR, skew, and kurtosis are, right? And then, of course, we would want to visualize these as well. And then these are just some images of box plots and histograms. So as a recap, our goal when we first get our data set should be to take a look at the individual variables in our data set and try to visualize them and also summarize them through the use of plots and charts and summary statistics. And then the last thing that I want to talk about really quickly is in this image right here, we can actually see the actual data points that go into making a box plot. And I don't know if I included that before. Let's take a look back. Yeah, so this box plot, I didn't show the actual data points except for these outliers here. This is how most box plots look, but as a side note, this is also a really good way of seeing how exactly box plots are calculated behind the scenes, right? So here we see the actual values, and so you can kind of see that the box, which is Q1 and Q3, well, from below the box, we would see the bottom 25% of the scores for the men. And then above the box, we see like the upper 25% of the scores for the men. And then the middle contains the middle 50% of the scores for the men. And then we can kind of see that with the women as well. So this is a useful way of seeing how the actual data points kind of go into determining how a box plot is calculated. But when you actually see box plots in practice, you will almost always see this form of box plot right here. But yeah, I hope this helps. All of the files can be found in my GitHub portfolio, which is linked in both the description and the About section. Also, I will be coming out with videos of how to find both the summary statistics and get all of these visualizations for descriptive statistics as well. I think those should already be posted by the time I load this. I have that for both SPSS software and R software. So those will also be on my channel. Feel free to check those out. And in those videos, I go over how you would actually calculate all of these in those two software platforms. So thank you and have an awesome day.